Okay, good morning and welcome everyone to today's webinar regarding the post-construction requirements of the NPDES Construction Stormwater General Permit. So, again, my name is Justin Reinhardt with the Division of Surface Water here at EPA. I've spent about the last 2 years working as the technical assistance staff for the stormwater program, focused especially on the construction stormwater permit. Today we'll cover for about 45 minutes or so various topics. We could probably spend a week talking about the requirements, and I could also spend an hour saying you shall do this and you must do this as the permit requirements say. But instead I'm going to try and give a good overview and background material to the post-construction requirements in the permit. You can obviously take a look at the permit, which is posted on our website, and look at a lot of the various nuances and details and nooks and crannies in that. We'll focus on background and in general terms how those post-construction requirements are and can be met, and have questions for the time for questions at the end, as Helen mentioned. Okay, so let's get started. Go back to the beginning and get everyone completely up to speed. What is the construction general permit? The construction general permit is part of the NPDES program, which is of course a product of the 72 Clean Water Act under US EPA, and it essentially discharges to waters of the state are authorized under permits. It can be an individual permit to a specific entity or point source, or generalized permits. And the general permits are crafted to cover activities that would, and quite simply, be difficult to individually permit because of the just vast quantities. Things such as household sewage treatment systems, pesticide applications, and stormwater applications that happen frequently across the state. So a general permit is crafted that gives essentially basic and general standards that need to be met in order to cover those discharges. Okay, so the general permits are usually renewed on a 5-year term or 5-year cycle. I've got the dates up there for the construction general permit. It was enacted in 1992, and it's gone through a couple of updates. Most recently, just this past April, the permit was renewed, and as often is the case with each of the renewals, some minor changes or major changes are made from time to time, updating various requirements. We did make a number of changes to the post-construction side of the permit there this past April, and actively trying to voice and educate people on those. So we won't cover the specific updates here, but they are included in today's webinar. Okay, so next question then would be, well, why an NPDES general permit for stormwater? Clearly, stormwater runoff, intentional or not, carries along the pollutants that it encounters on the surfaces to the receiving streams, to the point that can adversely affect water quality. So general permits create conditions that help to minimize and prevent those contaminants from reaching those receiving waters as much as possible. Permits are crafted to cover industrial facilities, small municipal separate storm sewer systems, or MS4s, which are going to collect a large surface area and drain that directly to a receiving channel, and all the stormwater and pollutants that would come with it. And construction activities, so we might have small to large areas of disturbances exposing a considerable amount of ground to erosion and transport of sediment and other pollutants along associated with construction activities. So that's what we're going to focus on today, the stormwater construction general permit. Okay, so who needs coverage under an NPDES construction stormwater general permit? Construction activities disturbing 1 or more acres of land, or are part of a larger common plan of development that will ultimately disturb 1 or more acres. So if you have a site that is maybe being phased in smaller increments or spaced in smaller increments that are less than an acre, but the sum of those parts is more than 1 acre, that would trigger coverage. The next question then obviously becomes, well, what are construction activities exactly? The permit defines them as clearing, grading, excavating, grubbing, and or filling that might occur. So you can sort of see anything that's going to disturb the surface to the point at which it's going to expose erodible materials are going to require coverage under the permit. Obvious exemption to that would be agricultural work, which has large areas of soils exposed for long periods of time. Okay, so what does the NPDES Construction Stormwater General Permit require me to do? Most simply, without going through all the nuts and bolts, it requires you to prepare and implement a stormwater pollution prevention plan, or an SWP3, or SW3P, or SWIP, and the many associated abbreviations and terms with that. And what a SWIP, as I'll refer to it from now on, does is it's a plan. It's a plan of action for implementing practices that are going to reduce and control sediment discharge and other pollutant discharges from the site. So it's going to include narrative instructions to contractors, forms, drawings as necessary depicting the design and construction of practices, the location of them, requirements for inspection of those controls throughout the construction process until the permit is closed. The SWIP is also a little bit different than a lot of plans in that it's meant to be a living document. So once the plan is enacted, it's anticipated that changes will be required as things happen like would happen on any construction site during the course of work. Things change, things need to be fixed, added, removed, moved, relocated, so forth. And the SWIP is expected to change along with that throughout the life of the project, whether it's 6-month construction or 10-year construction project. So what does a SWIP do? What's in a SWIP? In more specific terms, it requires controls be in place, as I've mentioned a couple times now, and those controls could be non-structural controls. It could simply be preserving certain areas. It could also be cordoning off areas that are for the purpose of protecting surface waters, wetlands, streams, so forth. And most commonly, people are familiar with the more physical structural controls that are put in place to control runoff and erosion as well as sediment. So things such as on the lower left, a settling basin to collect and still storm water and pull out some of the sediment coming with it, and perimeter controls such as silt fence on the right, shown on the right, and grass buffer areas to also filter and pull out sediment before it leaves the construction site. It also requires other pollutants be controlled, very common on construction sites, concrete, waste concrete from mixers, wash waters from mixers and concreting asphalt operations. Controls be in place so that discharge doesn't go directly into a stream, and other construction materials that are common to sites like paint, insulation, and things like that could trash that could possibly come up pollutant need to be controlled. And lastly, it requires post-construction stormwater controls. So these are controls that are going to happen after construction is finished and treat stormwater coming from the site for the length of the life of the development. You can see one here on your right. It looks like a bioretention basin, very common stormwater control before it enters the catch basin shown there and into the sewer network before discharging to waters of the state. So what I'm going to do is turn a little bit. That's the background on the permitting, how we got here story, and I'm going to turn direction a little bit and go through some post-construction tenets. Now, these don't exist anywhere written down in a manual or book or text, but things that I've come up with today to describe, again, without having to say the permit says this or the permit says that, what we're really trying to accomplish with what the permit does actually say, so that you'll have a better understanding and I think can then better implement practices when we get to putting things on the ground. And the first tenet here is a quote from NERP, which is not the video DJ of 1983's MTV, but the National Urban Runoff Program that happened in the early 80s. Was published in 1983, which is really the impetus for everything we're talking about today. And one of their conclusions that's often splashed about was that total suspended solids, or TSS, concentrations in urban stormwater runoff are fairly high in comparison with treatment plant discharges. So that's kind of like the headline grabber, and it indicates that TSS is a major pollutant loading in urban runoff. It gets amplified by the fact that that material in an urban scenario ends up being higher in mineral content and man-made products, asphalt, automobile substances are making up a lot of that solids, not simply clay, silt, and sand material. It's likely to have other contaminants absorbed to them: phosphorus, nitrogen, your nutrients, zinc, copper, lead, heavy metals, PAHs, aromatic hydrocarbons, bacteria, pathogenic pollutants, all end up sorbing or attaching themselves to those clay ions and sometimes the silt. A third part of that too is the TSS is identifiable, it's measurable, it's detectable, it's not reactive. So it's a benchmark that we can actually measure success on. And that leads to a benchmark which was really developed through the Coastal Zone Act Reauthorization Amendment in a decade later, in 93, which required of those coastal programs throughout the state removal of 80% of TSS as a benchmark goal. So you might ask, well, where does that 80% come from? And it really is the concept of, using US EPA terms, maximum extent practical, the MEP, or the best available technologies, meaning it's the best that we can really do. And that's evidenced, again, in the US EPA's report with the table I'm showing you here that shows various BMPs and their monitored pollutant removals. And you can see in that first column on the left, total suspended solids range anywhere from 30% effective to 100%. But by and large, many of them can be employed to reach 80%. So it was felt at that time that was the benchmark. That's where we needed to strive for, removal of 80% if we have a properly used, designed, built, and maintained practice, or best management practice. Okay, so let's go on to tenet number 2, which is, I think, encapsulated by this quote here from Wenzel in 1982, so about the same time frame that a lot of people were looking to study urban stormwater, which says the quality of urban runoff is so much more complex than quantity that it would be misleading to indeed attempt to use a single rainfall event of any type for design or analysis. It concludes that it really, urban stormwater requires the use of some effective form of continuous rainfall data. So what we're talking about here is not necessarily an event-based, which is a little counterintuitive to a lot of typical design engineering that is looking to establish a large-scale event. Really, an event is made up of a rainfall event, a precipitation event, of a lot of different factors, including the duration of rainfall, the total depth that comes to, and how that rainfall depth gets distributed over that duration. And those can be monitored from real-time data, which would be very incremental, so something that would happen. You would need to have something on a minute to 5 minute basis to demonstrate. More often, it's just synthesized into synthetic distributions and synthetic statistical interpretations of long-term rainfall data by various entities that get used in traditional engineering. So it's a very statistical process. It doesn't necessarily represent anything in reality, but what generally happens in the average. And that hydrograph that gets developed doesn't necessarily equal the plutograph. So what the pollutants coming off with that rainfall may be in concentrations that vary with the type of event, with the event, within that event itself, from the front loading of a first wash, first flush type concept, to thinking about how much loading and buildup was happening in the time period between events, so that maybe a small event after days of dry weather, may have a much higher loading than periods like we were in typically in spring, where we might have rain occurring every couple of days and limiting any buildup of pollutants. When you look at events versus a volumetric approach, here are two watersheds, area A and B, with a unit hydrograph shown for each of those. So you'll notice right away they're different shapes. They've got the same general area shown here, but different slopes, different just general configurations of the stream network, and they produce different hydrographs. Area A has a much higher peak flow coming off of it than B does. So now if we're looking at an event-based kind of process, it's going to vary from site to site based on all these site particular influences. But if you look at the area under the curve, that's the total volume of rainfall, it's independent of all that. So if we look at just strictly a volumetric approach or a volume capture, using an average pollutant loading through an event mean concentration or an average concentration, we can effectively say we can remove a certain amount of pollutants by treating a certain amount or volume of stormwater, and not necessarily a certain flow level like you might design for bridges and roads and culverts that are set to maybe a specific 100-year storm event, where flow is much more of a concern. Okay, so let's move to number 3. The fraction of rainfall is, when we're talking volumetrically here, is directly proportional to the amount of impervious cover. So this kind of ties into that same theory where when we look at just a volume, I can now fairly simply determine what I'm getting to my practice in terms of runoff from a rainfall event, regardless of the type of site that I'm dealing with. If I understand the amount of impervious area within that watershed, in this chart here, again from the late 80s and work by Schuler, which plotted the NERP data, and a number of people had fit curves to this, but the most universally used coefficient to transform precipitation to runoff is this R sub B value in this real linear equation here, 0.05 plus 0.9 times the fraction of percent impervious. You can see the more imperviousness, the larger that runoff coefficient gets, and the more of that rain comes as runoff as you would expect to see. Now, a lot of engineers are going to be familiar with the curve number methodology that the SCS built, and it takes into account a lot of different factors like soil types and what's happening in antecedent conditions, whereas this is very linear. Those things don't really get factored in because the imperviousness as low as 10% of the watershed imperviousness really outweighs all those other factors that the curve number method was built to deal with in a rural or agricultural setting. And you can see that if you look at the way the curve numbers are for a completely pervious or completely impervious area. They're very high to very low. Now, with that said, that 0.05 value is assuming that pervious ground is truly pervious, acting in a natural state with good soil structure, good topsoil, good land cover, as opposed to what happens in a lot of construction activities on the right side, where you have mass grading, topsoil removal, heavy compaction taking place, so that may be vegetated and considered pervious space or open space or green space, but it really is acting almost impervious as you have a very high runoff value. So we need to make sure that when we're looking at this, we're considering truly the double whammy effect of, are we getting the amount of runoff we're truly getting from these pervious areas, and are we maximizing the opportunity for treatment? Look how low that R sub B is. We can absorb a lot of stormwater on those pervious spaces if they're of good quality. So we'll talk a little bit more about that later. And tenet number 4, quantity and quality are closely related. They can't be separated for effective stormwater management. And that comes out of the ASCE text from 2012, the sort of current Bible of stormwater. And that is highlighted very clearly in a lot of the urban streams we see, where they are substantially downcut and eroded because of the volume of water coming to them. And that erosion in places can probably contribute as much or more TSS loading to the waters than the site is discharging itself. So quantity and quality have to be really considered hand in hand to really affect any change to the watershed and stormwater. Okay, so those are the 4 tenets. I went through them fairly quickly, but some things to chew on as we dive into the permit a little bit closer and talk about Ohio's approach to handling post-construction stormwater. And it's really fairly simple. In general terms, there are 3 requirements. The water quality volume needs to be captured. Treat that volume with an effective post-construction practice, and that practice should provide extended detention or infiltration of that water quality volume. So there's 3 real steps that all get married together in the design here of a post-construction practice. Let's look at the water quality volume. It's really a marvelously simple equation. You see we've pulled in the R sub B value, the fraction of rainfall as runoff, the area draining to the practice, or the area of the site itself to establish the required treatment level, because you could in fact put more than one practice on a particular site. So you could have one practice for one site, or you could have 2 smaller practices covering one site. And a precipitation value, which is given to you as 0.9 inches. So the question might come, where does that 0.9 inches come from? That ties into everything I mentioned earlier and brings sort of all those tenets home, that we're looking at a volumetric approach that is a continuous simulation of long-term rainfall data to assess how do we get to 90%, capturing 90% of that rainfall coming to us. That 90%, utilizing a roughly 90% effective practice, 0.9 times 0.9 gets us to 80% capture of our TSS loading. So to get 90% of the runoff volume, we actually need closer to 1.1 inches of rainfall to collect, but by simulating that rainfall through various practices, standard practices, we can take account for routing that happens, and that value actually gets reduced down to 0.9 inches. And I mention that because it's a frequent question to me as far as, what about routing? What about the reality of water coming in as water's going out? And you'll see as we get to it here in a second, the design process doesn't reflect that. That's because it's already built into the calculation into that 0.9-inch rainfall event. Okay, I don't know if any of you ever watched This Old House. One of my favorite segments of that was the what is it part, where you have these guys who are experts in their field sitting around trying to guess what some very specialized, odd-looking tool is, usually very comically doing so and coming up with explanations, and then you had to figure out who was right, what was the right use of the tool. And it kind of makes me think about stormwater practices, because they are specialized tools. These aren't the hammers and screwdrivers that are traditionally used in engineering, but they are these, whatever that circular widget is in the engineering world. They are meant to treat water quality, and as such, often require a little bit of a counterintuitive design and design principles. So let's look kind of at some of those practices that are our standard toolbox for treatment. Most commonly used are the surface basins, a dry basin, a wet basin with a permanent pool, or a wetland basin that's constructed. They all have advantages and disadvantages. The dry basins generally have lower effectiveness, and therefore the permit requires them to be amplified by using forebays and micropools to help boost that effectiveness. Wet basins are very good at capturing and retaining sediment in the pool itself. All of these practices have a long maintenance cycle, but eventually they will need cleaned out as they accumulate sediment. Wetlands are very good at treating water, but they're a little challenging in a stormwater perspective, because stormwater doesn't come to a wetland as its natural hydro period would want. So they tend to all be very wet or very dry and not get that cycle that a naturally occurring wetland would have. All these practices are very good at also combining in one place water quality treatment with flood control volume requirements. So you can see on the lower left example of an outlet structure that has two outlets, a lower, very small outlet hole on the bottom and a larger one on the top. So you would have a water quality level of treatment and a flood control level of treatment happening in the same place. So if you look at the design of these, this is where I say it's a little counterintuitive than traditional hydrologic and hydrology engineering. It's a pull-the-plug sort of scenario, or what I call it kind of a static drawdown. So you take that calculated water quality volume and you put that into the basin and draw it down through a controlled release. And that release has to happen at a specified manner of not more than the first half of the volume and less than the first third of the time. So why is that? Again, we're trying to promote settlement. We're trying to make sure that the velocity of the particles downward is allowing it to be less than the flow going outward, and we can capture the sediment that's suspended within that water column in that still basin. And the drawdown curve as such looks something like this. So instead of having a very steep drawdown and trickling out past 48 hours, in this case you've got a much more linear curve, really maximizing that settling time. There's a spreadsheet that's available on our website that produces this chart that can be used to check designs to see if they meet this requirement. The other question I always get with extended detention basins are the outlet designs. Outlets need to be protected because to control a release at that level requires a very small outlet or an orifice. Our rainwater manual, which I'll mention here, is our state design standards, has these images in it, the various types of outlets that can occur. On the right are the preferred outlets, which are drawing from a permanent pool in a wet basin or a micro pool. So they're pulling water from the center, making sure that floatables up top and sediment in the bottom can't clog the outlet. On the right, you see a picture of one that shows the problem with outlets. A lot of times, besides trash, is just that organic muck and gunk that accumulates at that water surface. And by putting something flat and horizontal and creating a lot of surface area, it creates a lot of area for flow to enter the outlet design and really maximize or minimize the opportunity for clogging. Yeah, on the right, you see where we're drawing water from a pool, preventing the floatables and on the top and sediment from entering. The problem with, and the big discussion point at this time of the year, or as we're leaving this time of the year, winter, often also comes in freezing. You have a pool of water in cold sub-zero temperatures are going to freeze, especially in the water's confined in a pipe in a small area, fully exposed, like at these 2 points within a riser. So that's the upper right drawing is probably the better practice for reducing the effects of freezing, and that water is not sitting in that pipe. Another question and issue that's come up is use of plastic pipes that are maybe a little bit more fragile in those settings. Unfortunately, all of our designs are going to be susceptible to that in our weather. Infiltration practices are an option. So we have here a basin on the left or a trench on the right. So if we have soils, especially hydrologic soil groups B and C's that have a very good, more than ½ inch per hour saturated conductivity, we can put that stormwater back where it wants to go originally, which is into the subsurface, by storing it into over an infiltration bed, both laterally and downwardly over a period of time, infiltrating that water. We don't want it to sit too long so that we've got a mosquito or a nuisance problem. Most people are looking to have this be relatively dry. Maintenance is a challenge on these too, is that water may sit and that ground may be soft. So if you have something at the basin as on the left that's going to be in turf grass, mowing during the wrong time can really create a lot of problems as far as rutting, compaction, and just disruption of the design of that basin. So again, what we're trying to do is infiltrate water in a given surface area. So two things need to happen in those scenarios. One, we need to make sure that infiltrative surface doesn't get clogged by the sediment that's coming with it, especially the clays and silt. So we need to have pretreatment of the stormwater entering it. So maybe on the left you've got sort of a filter strip I've shown of grass before sheet flow enters into the basin. We also need to make sure the basins aren't overloaded, so there are minimum requirements there. Generally, more than 5% of the impervious area as far as the area that infiltration basin goes, or the bottom of the practice. Permeable pavement is a little bit different in that if we got run onto the infiltrative area, it needs to be no more than twice the pavement area size. We can also have filtration practices with extended detention. So these are the mechanism here for treatment is simply filtering via the paver, pavement, and sublayer systems under the permeable pavers to your right, a sand filter down on the lower right, which we don't see a lot of in Ohio, and I had to steal a picture there from southeast Michigan. Not commonly used. Can be maintenance challenges, but are very effective at treating stormwater. On the other side of the scale, are very commonly used more and more as we see more dense urban area or ultra-urban development with underground practices, a detention basin, be it some sort of vault chamber, arch pipe, stone-filled cavity where you're storing that water underground and detaining it, very similar to a surface basin. It doesn't have all that extra good treatment. You get the biological stuff, the soil interaction, the UV type treatment. So we require pre-treatment happen to pull out sediment before it enters the detention basin. And then you have bioretention, which I kind of give it as its own category here, because along with the other practices I just showed you, which can be also used as infiltration, bioretention can sort of go both ways. It's a very versatile tool. You see 4 different basins here, or bioretention areas. Up on the upper left, a grassed area that blends well into the landscaping with a turf grass cover. In the lower left and the upper right, you've got bioretention areas built into the parking lot areas and the dividers and the islands. And of course on the lower right, using maybe setback areas or designated landscaping areas to incorporate bioretention. You see different plantings, so grasses, shrubs, turfs can all be used as the vegetative treatment in bioretention. The things I want to sort of highlight with bioretention, again, similar to underground systems, it's very important that we have pretreatment so that we pull out sediment from clogging that treating media, which is the planting soil shown here. That planting soil needs to be very specific. If it's too sandy, nothing will grow in it. If it's too organic or too topsoil, it won't filter and drain. So the recommended mix is a 5:1:2, or about 60 to 65% sand. That needs to be a clean sand, not a gravelly sand or concrete sand, but much more like you'd see in a playground type scenario. 12 to 13% topsoil, so you need some nutrients for the planting material to grow in, and up to 25% organic matter. It provides a good growing media, porous, permeable, and filtering. And those practices, again, can be put over D-type soils, very tight, non-draining soils, utilizing an underdrain on hydrologic soil group B and C soils. They can work well to just infiltrate straight through the bottom. And on A soils that take a lot of water, we can infiltrate them, but probably need to think about putting a sand layer or some sort of additional protections on the bottom. Show you here just a picture of what that underdrain might look like. We have very detailed drawings and requirements in the rainwater manual that goes through some of these designs. This is just a good example of showing you how they have versus the other drawing where you'll have a gravel encased underdrain to drain the bioretention in cases where you won't get the infiltration you're seeking. Otherwise, you're going to have a wetland or a wet detention basin, which would, in most cases, be a failure. Okay, so I've mentioned a couple times now that all of these practices, the design requirements of them, recommendations, guidance, and requirements are all listed in the Rainwater and Land Development Manual, which is the state's stormwater manual. It is online on our website. The address is there. It's a little bit difficult to navigate, so I'm showing it on the lower right where that link is. You'll also see here there's a number of other different documents, and this will be growing as far as technical assistance type documents goes, hopefully through the coming year and beyond, and being able to provide information. I also do, while I have it up, want to highlight to you there are a couple spreadsheets, including the one that produces the chart for the detention basin drawdown I showed you earlier, it's listed as a water quality volume compliance spreadsheet. Of course, those are the state requirements, and I mentioned there's a permit for the small MS4s as well as the phase 1 communities. They may have requirements that supersede or exceed, I should say is the proper term, the construction general permit requirements. So working in those areas, you need to be mindful of the local stormwater regulations, and many of those communities have manuals built that are built off of the state stormwater manual, and need to also be considered as you're working in each of these areas, be it a municipality, a county, township, and some other areas. So a common question that would come up at this point is probably, well, are there any exceptions to all this? And to I guess, litany through some of the permit language, there are some circumstances at which need to be considered. One, very easily, if a project isn't going to create any impervious area, post-construction requirements practices aren't required. Linear projects, so highway, roadway design, very challenging often to implement requirements, post-construction practices. They are still required, however, some flexibility is given in that you may utilize the location design or the L&D manual, how's the ODOT. Redevelopment site, so a site that already has been developed and is going to be redeveloped into a new use. There's a little bit of a different water quality volume calculation there that takes into account the existing impervious area and provides credit to that. So through that, there's a reduced water quality volume requirement that we can make sure that we're promoting the use of redevelopment as opposed to sprawling into undeveloped areas. There's flexibility built into the permit for the smaller sites, and by smaller I mean under 2 acres. So the permit trigger I said in the beginning was 1 acre. So if you're in that 1 to 1.999 range, we recognize that those sites are often challenged for space, and it's possible there to justify alternatives to those standard practices and designs. If again it can be rationalized, and that needs to be recorded in the SWIP. Ultimately, our guidance and recommendations are to follow the water quality volume and the standard practices, as those are the ones that Ohio EPA believes best meet the water quality standards in Ohio. But if you were to, on those smaller sites, there's some flexibility for it to come up with your own way of trying to meet those standards, but again, we really look at the water quality volume approach as being the best way. The new permit also added runoff reduction practices, so those can actually reduce the water quality volume, again, getting back to what I talked about with the pervious space and R/B, by using those pervious areas to really do a lot of stormwater treatment. So if you look at a typical site development of maybe 2 acres with 1 acre of parking impervious pavement here, general design would be to put that catch basin and storm sewer network on that pavement itself to immediately collect all that runoff water and keep it from flooding and creating nuisance ponding in puddles. And all the grass is effectively doing nothing in this case, but being mowed. Well, if we calculate the water quality volume requirement for that base scenario here, just as an example, it comes out to about 0.075 acre feet, the treatment required in a practice that would need to be installed for that site. But if I were to disconnect that impervious area and have it sheet flow into my practice through a disconnection, through a grass filter strip, through a grass swale, I can then take reduction for the work that pervious space is doing for me. We do have a spreadsheet to calculate it. I know you can barely read this, but I just wanted to show you what it looks like so you know you're on the right sheet. You can get to it from the web page I showed earlier, or just contact me and I can get it to you. And I can use that spreadsheet to calculate. I've got a disconnection. I've got sheet flow off of my pavement, and I've got a swale now instead of a pipe taking all that water to my practice. And I reduced my requirement from 0.075 acre feet to .047, so not half, but I've knocked a third off my requirement, which shrinks the size of my practice. Now, hopefully, I've also saved money on the size of my practice, but also reduced costs from not having to install the catch basins and associated piping with that. So there's probably a lot of different benefits if the reduced water quality volume isn't sufficient. Those practices could include, like I've mentioned here, disconnecting pavement and roof areas, enhancing those disconnections in areas that may not infiltrate well with things like stormwater planter boxes or on the right, or rain gardens on the left. Grass swales, which I mentioned, which would be just a trapezoidal, not a traditional drainage ditch, but a trapezoidal conveyance channel. Sheet flow areas to design grass filters or conservation areas, which is the same as a grass filter, just vegetated with maybe thicker grasses, unmaintained, trees, shrubbery, etc. Shown there on the lower left. Okay, so with that, I'll just sort of wrap up that whirlwind tour of post-construction with just a couple of quick thoughts that hopefully summarize everything. Points to leave you with are really that the post-construction requirements in the permit are, if you look at my A, B, and C listing there from the previous slide, are pretty basic and quite simple considering what we're trying to do, which is chemically, physically treat stormwater for pollutant loadings. But that's often an unfamiliar process. It doesn't follow traditional engineering paths, as I tried to highlight. So it does take specialized skill and specialized practices to use. The permit does create a lot of flexibility for designers to minimize the effects of stormwater by doing careful site planning. So the runoff reduction credits and other things really afford a lot of flexibility to the developer and designer. It's not everything is very cookie cutter. It doesn't have to be very cookie cutter. And with that said, the most successful sites end up happening when that process of the stormwater control is being discussed and designed and incorporated early in the design process. So I realize that's often not the case, that those things get fit in around the more interesting and money-generating parts of the development, which is the infrastructure, the buildings and associated parts, and the spare spaces that get used for stormwater treatment. But the more we can integrate in the upfront part of the design process, I think the smoother generally it is to try and meet the water quality goals. And with that said, I'll just say that I'm available for information, help with any of that at any time. My role is technical assistance both to our internal permitting staff you see on the top in the various parts of the state, as well as external consulting engineers, developers, communities, corporations. If you need any type of project assistance, let me know. Specific training, we can do that. And I also have our administrative staff who, if you have NOI type questions, submittals, where's my permit type questions, feel free to contact any of our staff there. And many of you know John Matthews, who I've worked with for a number of years as our stormwater group manager.
Okay, our first question is, how is Ohio EPA evaluating potential impact to groundwater from infiltration practices?
That's a bit of a common concern with infiltrative practices, the pros and cons of trying to get stormwater in the ground without where it wants to go, like I said, without doing further damage by exporting those pollutants with it. So we need to first of all make sure that the practices being installed are successful in treating that stormwater. We're also making sure we're not using infiltrative practices in the hotspot areas. And hotspot is just a general term for things where we may have excessive particular pollutant loadings. Gas stations tends to be a common one to visualize, although they generally have a lot of controls and protective measures built in themselves. But that type of scenario, we're looking to try and avoid those areas. As far as evaluating impacts, I don't know if there's necessarily an evaluation process as much as just trying to prevent as much as possible through proper recommendations, guidance, and installation to make sure that we're, like I said, if we're on those A-type soils that are going to pull water into the ground too fast, that we're incorporating additional treatment and protective measures like a sand layer underneath them.
Okay, are you required to use the standard practices?
So the the permit spells out a list of pre-approved practices, and there's two tables, 4A and B, that list the practices that are standard, very effective practices that can be used and must be used. Again, unless you're under that 2 acres, and there's a little bit of a possibility to go other directions. There is also an alternative process where an alternative design could be proposed. It's not really well utilized because there aren't a lot of other practices out there that really fall into that category that can be effective, can provide the extended detention volume, but that out clause sort of is in the permit to allow in case something new does come along or something really innovative does come along on a particular site that we could, certainly consider it without having to wait that whole 5-year permit cycle to change it based on some new information.
Okay, that's it for our questions. So we are going to go ahead and wrap this up. Again, we appreciate you attending today. We do have another question that just came in. How are the new requirements reconciled with the existing county or municipality regulations that have not been updated to meet these new requirements?
That's a sort of a catch-22 because we have the permit was modified here in April. Most of the local level folks are still utilizing regulations based off their MS4 permit, which is kind of a cycle behind. We're hopefully going to try and get those permit cycles to kind of match up a little bit better at some point into the future. But right now we're expecting the local counties and municipalities to upgrade their regulations to be equivalent to or exceed the permit requirements. So there's a little bit of a technical discrepancy there, and that a lot of those regulations take a little bit of time or get forgotten about and don't necessarily get regulated. But the construction permit does still hold its authority.
Okay, great. Well, thank you. Thank you for attending today. And again, if you could just take a couple minutes to complete our evaluation when you exit WebEx, we would appreciate it. And if you have any questions, please feel free to contact the district permitting staff or, as Justin said, the technical assistance staff. And when I send out the follow-up email with the recording link, I'll also send Justin's email and phone number as well. So thank you, and you folks have a great day.